Hello, everybody. We continue our lectures. Last time we studied properties of Markov chains. For example, we calculated expectations, probabilities of hitting certain sets, and we also studied generating functions. And now let Xn be a Markov chain on a finite set E, and transition probabilities Pij, and transition probabilities in n steps is Pijn. At first, I would like to calculate generating functions Uij of s, which is equal to sum over n Pij n s to the power n, and the matrix U of s will be the matrix of this Uijs. Note that these probabilities are bounded by 1, so this sum is convergent if s is less than or equal to 1. Also, let me introduce the probability Fijn, probability that a point J is visited at the first time at the nth step if you start from I. So probability that x0 is not J, x1 is not J, so on, xn minus 1 is not J, and xn is J, given x0 is I. And Fij of s is sum of Fijn s to the power n. This probability is smaller than this one, so this function is well defined also for s less than 1. By definition, I always assume that Fij of n of 0 is 0. So this is our agreement, and let me recall you that pi Aij of 0, so visit j at 0 set if you start from I is equal to 1 if I is j, and 0 if I is not j. Let me recall your relation between Pi and Fi. So we start from I. At the nth moment, you are at j, and let sigma j be the first instant. So is the hitting moment x of k is j. This is sigma j. So the probability Pijn, so you are here at the nth instant, is equal to sum of probability. Sigma j is 1, sigma j is 1, and so you first time, so let me write Pijn is equal to sum k from 0 to n probability that sigma j is k and xn is j, well, and start from I. Observe that these events are disjoint. And if sigma j is k, then you start from j and you end at j, and probability that sigma j is k is equal to fij. So you start from I, you hit j at the first time. So this probability is equal to sum fijk and times p jj and minus k. And this sum reminds us convolution of sequences f and p. Well, this equality is true for n greater than or equal to 1. If n is 1, Pij is equal to indicator. Okay, so let me rewrite this formula once again. Oops, I'm sorry. Something happened with my screen. Okay, let's continue, and I would like to rewrite our important formula. Pijn is equal to sum fijk times pjjn minus k if n is greater than or equal to 1, and Pijn is equal to indicator that I is j. Observe that this sum is equal to 0 if n is 0, because fij0 is 0 by definition. So if I is not j, Pij0 is 0, then we have that Pijn is a convolution of sequences f and p. If I is equal to j, then Pij is a convolution of f and p except of the first term. And we know the generating function of a convolution is a product. So Uij of s is equal to Fij of s times U j of s, and minus indicator that I is j. So if I is not j, we don't need this. We have just a convolution. If I is equal to j, we have to subtract the first element. And
Sorry,
or plus? Yeah, plus, excuse me.
sorry, we should not maybe write pi EIGN in the second line.
Oh, 0. So, yes, thank you, Igor. No, no. One moment, let me think about. Yeah, let me think, plus or minus. Yeah, yes, with plus, certainly, yes. So Fi j of s is equal to ratio Uij of s minus this indicator over U Gj of s. And now let me explain you that calculation of U is very simple. Indeed, what is Uij of s is equal to sum of Pijn times s to the power n. And the matrix Pijn is nothing else as matrix transition matrix in n steps, or we know that this matrix is equal to matrix P transition probabilities in one step raised to the power n. So the matrix U is sum of matrices P to the power n, S to the power n, and we know that the series convergence is convergent if S is less than 1, and it reminds us geometric series, and the answer is this: identity matrix minus SP and calculate inverse matrix. So this is homework. Prove this equality. So U is easy to calculate. You just calculate 1 minus SP and inverse, and this also reminds us resolvent of matrix P. So we know U, we have this, and when we have this, let me show you few important corollaries. The first corollary is this. Let A be a set. You start from certain point I, and I would like to calculate the following expectation. Expectation, you start from I, some s to the power sigma a and g at x at the moment sigma a, where sigma a is the heating time. So what does it mean? U walk until you hit this set, and then you calculate this expectation. For example, if G is indicator, so if you know this, then you know the joint probability, the moment of hitting and the instant of hitting. And if G of X is equal to indicator X is J, then you calculate generating functions that of sigma A given you enter set A into, and when you enter, you jump into J. So what is this? This expectation is equal to sum probability times value. Probability that sigma A is K, and X sigma A is J, and S to the power, excuse me, N, S to the power N, G of J, and what is this? This is F I J N, and we have to calculate also sum over J in A. So this sum is equal to sum over J, sum over N, F I J N, S to the power N, G of J. And observe that G is independent of N, and this is our generating function, Fij of S. So the answer is sum over J, Fij of S, G of J. You can think about this as following. You walk until you hit A. When you hit A, you obtain, if you enter at the point J, you stop the walk and obtain G of J money. But there is inflation, and each time there is some discount S times. So after n steps, the discount, the inflation is S to the power n. So this is your average profit of the walk if you discount money after each time. Well, and the second application is recurrence and transience of Markov chains. And recall that state J is recurrent if probability that sigma of J is less than infinity is 1. So if you start from J, then 100% you return to J. This is definition. And now let's try to calculate this probability. Well, this probability is equal to sum n from 0 to infinity fjj n, or fjj of 1. Let me recall you our result about relation between f and u. Now I is j, so this indicator is 1, So for every s in 0, 1, 1 is not included, we know that fj of s is equal to ratio ujj of s minus 1 over uj of s. However, this series is a series of non-negative numbers, and the same is for s. So by monotone convergence theorem, uij of 1 is equal to limit of uij of s as s tends to 1 from below, and the same is for u. And if this sum is infinite, then the limit is infinite also. We know that f jj of 1 is finite, and because it's less than 1. And it's equal to this limit by monotone convergence theorem. And we know that it's equal to the limit of ujj of s minus 1 over ujj of s. And this limit is equal to 1 if and only if numerator and denominator converge to plus infinity. So limit of ujj of s is plus infinity. Otherwise, the limit will be strictly less than 1. Or u of 1 is infinity, or the series, what is ujj of 1 is series pjjn is divergent. And j is recurrent. So we proved well-known criterion of recurrency using generating functions. Now, small application. Assume that
Can you go back for 1 second?
Well, I forgot to say, well, E is finite or countable. So everything works if E is countable also. And our next example will be a simple random walk that jumps P with probability P to the right one and with probability Q to the left. So state space is Z, and assume that you jump to the right with probability P, and you jump to the left with probability Q, where P plus Q is 1. And let's find conditions of transiency and recurrency. So the state J is recurrent. If and only if some p j j n is divergent. And in this case, we calculated this p. We have already calculated this number. So we start from j, we return to j, and it is possible if n is even number. So I will calculate only pjj n, and we make n steps up and n steps down, and the answer was to n choose n, p to the power n number of steps up, and q to the power n. So to n factorial over n factorial squared pq to the power n. So this statement is equivalent to the following. Sum over n from 0 to infinity. I recall that all odd probabilities with odd n are zeros. So to n factorial over n factorial squared pq to the power n is infinite. And let me recall you Stirling formula that n factorial is equivalent to square root of 2 pi n over e to the power n as n tends to infinity. So to n factorial over n factorial squared pq to the power n is equivalent to square root of 2 pi times 2n to n over e to the power 2n. Now denominator n factorial squared, so 2 pi n, 2 pi n small, 2 pi n without square root.
The power also n small.
Ah, yes, also small n, times n factorial squared, so n over e to the power 2n and pq to the power n. Well, n to the power 2n, n to the power 2n, so you may cancel this n. Now e to the power 2n, e to the power 2n disappears. 2. So 1 over square root of pi n times 2pq, 2pq to the power n, or 1 over square root of pi n, 2p times 1 minus p to the power n. Well,
Excuse me.
yes.
We had 2 in the power 2n. Yes, or
Oh, yes, exactly. 4p 1 minus p. You are absolutely right. And now make a graph of function for p 1 minus p if p between 0 and 1, and you will see parabola, and the maximal value of this parabola is 1 if p is 1/2, and if p is not 1/2, then this is strictly less than 1. And we see that this series is divergent if and only if p is 1/2, and then we have series square root of pn, which is divergent. If p is not 1/2, then the series is convergent. And we got well-known result that this series divergent if and only if P is 1/2. And the next question is the following. Okay, what happen if you consider the general random walk? Because if you consider, for example, the walk with probability, say, P to the right, Q to the left, and R, you stay at the point, then there is no such nice formula as before. And if the chain may make 2 jumps, 3 jumps, 5 jumps to the right, then there is no chance to find nice formula like this for probabilities. However, in case of random walks, there is a way to find these probabilities Pijn. Well, not them, but the generating functions. Okay, so now another example. Xn is equal to initial position x plus sum k from 1 to n psi k, where x is integer and psi k are integer valued independent identically distributed random variables are integer valued I independent identically distributed random variables. Well, I wish to calculate the probability xn is y given x0 is x. And this probability is equal to probability that sum of psi k is y minus x. And this sum will be denoted by s psi of n. So by definition is sum psi k from 1 to n. Okay, so this is equal to probability that s psi of n is y minus x. Well, there will be no nice formula for this probability, but it is possible to calculate a generating function. And I would like to recall you the definition of characteristic function of a random variable. Phi xi of z is expectation of e to the power I xi z, where I is square root of -1, and recall that xi is integer valued random variable, so this expectation is sum over all let me use theta. Sum over all k in z, probability that xi is k, e to the power I k theta. And this is Fourier series. By the way, if xi is integer value, then this function is periodic, and period is 2 pi. And what is characteristic function of xi1 plus xin? These random variables are independent, identically distributed. So since they're independent, then characteristic function of sum is equal to product of characteristic functions. And since they are identically distributed, then characteristic function of sum is equal to characteristic function of one random variable to the power n. So this is characteristic function of s psi of n of theta. And on the other hand, this is equal to sum over all k in z, probability that s n is k, e to the power I k theta. And now we are ready to calculate sum over n pxy n s to the power n. So sum of p probability that xi of n is equal to y minus x s to the power n, and this is equal to u x y of s. Oh. Okay. And my next question is, well, assume that you know Fourier series. Is it possible to calculate this? And if yes, then what is the formula?
We need the inverse Fourier transform.
Well, this is Fourier series. This is not Fourier transformation.
Yeah,
And what is the
but
formula?
we need to multiply by e to the minus ik theta.
Yes. And
yeah, and take the scalar product, so the integral.
so really, you have to multiply by e to the minus I chi theta. And what are the bounds of integration?
So the period
Mhm.
of our function from 0 to 2 pi, or
Yes,
yeah,
or from
minus
negative pi to and
we also need some multiplication by the
yeah.
the length.
So if you forget this formula, then just make some calculations. So if you have a function psi of s is sum of alpha k e to the power I k theta, and if you multiply psi of s by e to the minus I say j theta and integrate from minus pi to pi, oh theta, sorry, theta, d theta, what will you see? Well, let me make formal calculations, and this formula, the formula we obtain, is well known from mathematical analysis or from functional analysis. Alpha k and integral from negative pi to pi e to the power I k minus j theta d theta. And if k is not j, then this is 0. So it's easy to calculate. So in this sum, only one term may be non-zero, the term when k is equal to j. And if k is equal to j, then this is 0, e to the power 0 is 1, and this integral is 1, so we have 2 pi. And now we continue our calculations. This is equal to sum over n.
Can you please recall the derivation of this blue part? So what do we start from?
Okay, we start from ux y of s. This is the generating function, some p x y n s to the power n. Then I just recall this, and I recall that this probability is integral 1 over 2 pi, integral from negative pi to pi, characteristic function e to the power minus I, and then y minus x theta d theta s to the power n. And now recall that this is a product. This is a product of characteristic functions. So characteristic function of psi to the power n. Let me write s to the power n here. E to the minus I y minus x theta d theta. And absolute value of this is less than 1 if absolute value of s is less than 1. So phi psi theta s to the power n is less than 1 if you have this. So using Fubini theorem, we can interchange sum and integral if absolute value of s is strictly less than 1. So it's equal to 1 over 2 pi integral from negative pi to pi sum and from 0 to infinity pi xc of theta s to the power times s to the power n times exponent minus I y minus x theta d theta. And now this is geometric series. So this is equal to 1 over 2 pi integral from negative pi to pi e to the minus I y minus x theta 1 minus s phi psi of theta d theta. So look at this beautiful formula. We obtain this as certain integral. Well, certainly we need to be able to calculate this integral, but it's easier to study integrals than infinite sum with unknown probabilities. So let me rewrite this important formula once again. So ux y of s is equal to 1 over 2 pi integral from negative pi to pi minus I y minus x 1 minus s characteristic function of psi d theta. The first question, is this function continuous if absolute value of s is 1? Yes, there is no problem. Denominator is never 0 if s is here, because absolute value of phi is less than or equal to 1, so absolute value of this is strictly less than 1, so 0 is not denominator, so this is continuous function. Oh, I forgot to write here theta. So this is just Riemann integral. This is Riemann integral. You have to be careful because this is a complex number, and 1 divided by 1 minus s times complex number, so you have to know how to calculate the inverse, but this is not a problem. On the other hand, this is a real number. Indeed, this is a real number if s is real. And when we calculated all these integrals, so they were probabilities. So this integral is probability. So actually, this is not only real number, but also non-negative number if s in 0, 1. So I may write the following, 1 over 2 pi, real part, integral from negative pi to pi, e to the e y minus x theta 1 minus s phi psi of theta d theta, and I can integrate real part of this term. We know that imaginary part disappears, so sometimes it's easier minus x theta. Oh, I forgot minus 1 minus s phi psi of theta d theta. And now let's discuss recurrence and transience. So ux x of 1 is infinite if and only if limit as s approaches to 1 u x x of s is infinite if and only if limit s converges to 1 integral from negative pi to pi real part of, well, in this case y is x, 1 over 1 minus s phi psi of theta.
Excuse me.
Yes.
Is it what we wanted? We have equal 1 and equal
Oh,
infinity.
plus infinity, plus infinity. Thanks. Plus infinity. So x is recurrent state if and only if. And if and only if this is equal to infinity. So we proved the following beautiful result. So instead of talking about infinite sums, which we don't know how to calculate, we have to prove that the limit of integrals is divergent. Well, it's tempting to say that this happens if and only if integral from negative pi to pi, real part of 1 over 1 minus phi psi of theta d theta is plus infinity. However, we need to discuss this statement. At first, this is a complex number. This is a complex number. We take real part and we discuss convergence of integral. The first question is this. Is it positive number, negative number? May it take positive, negative values? The answer, this number is non-negative. So real part of this belongs to 0, okay, 0, infinity. Indeed, absolute value of this is less than or equal to 1. So 1 minus, so this is complex plane, 1 minus this number belongs to the following circle of radius 1. And if you calculate the number 1 divided by this, then this number will be here in this half plane of the imaginary plane. So this number, so real part, is non-negative. Well, it might be infinity. For example, if theta is 0, then characteristic function is 1, then this number is infinity. So this is the integral of non-negative function, and the question is it convergent or divergent? Well, and all these numbers are also non-negative. Well, actually, they cannot be infinite, and 0 also. So these are integrals of non-negative functions. We know that this function converge to this function for every theta. And we wish to pass to a limit and to say that limit of integrals is equal to integral of the limit. Actually, this is a question, and the interesting problem is, okay, homework. Assume that psi is 1 with probability p, psi is negative 1 with probability 1 minus p. Is it true that limit of integrals is equal to integral of the limit. Well, you may easily calculate characteristic function and calculate the integral explicitly and then pass to a limit. So just try to prove. And the well-known result is this, that this is true. So the answer is affirmative. So this is true. And let me write this as a theorem. We will prove one direction, and the other direction is very complicated, and the reference is, for example, Spitzer book, Principle of Random Walks. So famous book on random walks. But one direction I can prove easily. So uh, mm, and the hint is this. Well, all of these numbers are non-negative, and limit of this is equal to real part of 1 minus phi of theta. And what is the inequality between this, and who proves the corresponding theorem? So I have to write this inequality or this inequality.
So this is Fatou lemma.
Yes.
And
less the second one is true. Less or equal. No. Sorry. I thought about upper limit.
Yeah. So this is greater than or equal to this one. So if this is convergent, so if okay, if x is transient, then limit is finite, and then integral of the limit. By the way, we know that limit exists. Limit is finite, So integral from minus pi to pi, real part of 1 minus phi of phi xi of theta d theta is convergent. So if divergent, then recurrent. So we proved one direction. Another is a complicated result, and I don't have a time to prove it. And let's consider examples. Okay, another problem for homework. Find theorem. What happens for random walks in multidimensional integer-valued random walks in multidimensional space? So investigate recurrence transience of random walks in z to the power d and try to prove some analog of this result. What will be different? And okay, examples. Let's consider symmetric random walk at first. Then phi psi of theta is equal to probability 1/2 times e to the power e theta times 1 plus 1/2 times exponent e times -1, e theta times -1, e this plus e minus I theta over 2, and this is cosine of theta. And the integral of the real part of 1
Sorry,
over...
I have something strange with sound.
Oh.
Igor, do you hear?
I can hear well.
Is the sound okay?
Yes, it's okay.
Okay, then it's from my side.
Okay, so the criterion is this. We have to study this integral. By the way, we may not write real part because this is real number. And we know that cosine theta is... So there is only one suspicious point. Theta is 0. And in the neighborhood of 0 cosine... Okay, let me write Taylor formula. So 1 minus cosine is theta squared over 2 plus O small of theta squared. And 1 divided by this is equivalent to 2 over theta squared. And we know that integral of 2 over theta squared is divergent because 2 is greater than 1. So we get this. And we prove the recurrency if the random walk is symmetric. Well, now let's consider the case when xi is 1 with probability p and xi is -1 with probability q. Then phi theta is equal to p e to the power I theta plus...
Can we make a 5-minute break?
So this is the last example. almost. So I have two examples, Vadim, and I will finish the lecture. Is it okay?
I suppose Vadim asks because he has problem with sound.
Ah. Okay, let's make 5 minutes break.
It's okay. I will watch the recording.
Okay.
I just have some problems with sound.
Okay. Then 1 divided by 1 minus 5 of theta is equal to 1 over 1 minus p e I theta minus q e to the minus I theta is equal to, well, but this is imaginary number. So let me write it like p cosine theta plus p plus ip sine theta and minus q cosine theta minus I sine theta, and this is equal to 1 minus p plus q, 1 minus cosine theta plus I sine theta and multiply by minus q minus p. Q minus p sine theta. Well, let me multiply numerator and denominator by the conjugate number. So 1 minus cosine theta. Then the result will be this plus q minus p squared sinus t squared. And numerator will be 1 minus cosine theta plus I p minus q sine theta. Oh, and let me calculate real part. Real part.
Excuse me, maybe
Yes.
in the denominator minus I. If
There is no I in the denominator.
I mean
Here,
yes, yes.
I wrote pi minus q. There was q minus pi.
Yes. Thank you.
And after writing real part, this term disappears. And this real part is equal to 1 minus cosine theta, 1 minus cosine theta squared, plus q minus pi squared, sine squared of theta. And so if I don't make a mistake, something. Yes. And again, denominator is equal to 0 if theta only if theta is 0. And what is the asymptotic of the numerator and denominator if theta goes to 0? We know that asymptotic of numerator is theta squared over 2. Asymptotic of this is theta to the power 4 divided by 4. And asymptotics of this is theta squared. Because sine of theta is equivalent to theta. So there is a limit of this function as t approaches to 0. And hence, the integral of this is convergent. And we got we get transiency if P is not Q. So P, I forgot to say that P is not Q. And in this example, you may see that, well, you have to operate with complex numbers. And in order to calculate this number, you have to multiply by conjugate and to think a little bit. And the last example of maybe theorem is this. Assume that xi is integer valued random variable with finite expectation. If expectation of xi, okay, then as xi is recurrent, if and only if the expectation of xi is 0. And sketch of the proof is the following. We consider only the case when xi is symmetric random variable. The general case can be considered similarly, but with more details. And if xi is symmetric, then characteristic function of xi is real valued. Okay. Now, since expectation is finite, we know that phi xi is differentiable. Phi xi is differentiable. And we know that its derivative at 0 is equal to I expectation.
Excuse me.
Yes.
Can you please recall what is S psi from the theorem, from the condition of the theorem?
Just random walk. S psi of n is xi1 plus xi2 plus xn. So we just consider random walk, we add the same random variables every time.
Yes, sorry, just confusing because recurrent we used for the states, and now it's the whole walk. Okay.
Ah, yes, but you see, thank you for telling me this. And so the state is recurrent if and only if this integral is divergent. And this integral is independent of x. And indeed, the probability that you start from x and return to x is the same as if you start from 0 and return to 0. So if you consider random walk, then all states are recurrent or transient. So all together.
Yes, indeed. Yes, thank you very much.
And now let me write Taylor expansion of characteristic function in a neighborhood of 0. So it's 1 plus I derivative at 0 expectation of psi theta plus O small of theta, and real part of 1 over 1 minus phi psi of theta is equal to okay, I'm sorry. So forget about this. Forget about this. Because if it's symmetric, then expectation is 0. So it's real part 1 plus I expectation of psi theta plus O small of theta. And now let's multiply and divide by conjugate. Real part 1 minus I expectation of psi theta plus O of theta conjugate number. So I don't know, is it real or complex or imaginary? And here will be 1 plus expectation of psi squared times theta squared no, excuse me, 1 minus this. I expectation of psi theta plus O of theta, something like this.
Sorry, maybe minus
With
before
minus, yes.
no, I mean left. One minus and bracket. Left, a little bit left.
Here?
Yes, we have one.
Yes, 1 plus this and
No, still not. I mean, we have one minus characteristic function, and you have characteristic function in brackets.
oh,
Oh,
yes. Yes, you are absolutely right. Thank you. So generally, we obtain this expression. Well, we have O small here, but let us multiply and divide by the conjugate number. E expectation of psi theta plus O small of theta conjugate, and denominator is expectation of psi times theta with I plus O small of theta squared, the absolute value squared. And the real part of this is the real part of O small of theta conjugate or without conjugation divided by absolute value of I expectation of psi theta plus O small of theta squared. Well, if we know, so this result is easy to prove is phi xi is differentiable 2 times, then you may write Taylor expansion up to the second order, and in this case this O small of theta looks like theta squared times some coefficient, and if this is not zero, then it's easy to see that this integral is convergent. If xi is symmetric random variable and the expectation of xi is immediately zero, and O of theta is then real valued function, then in this case we have that this real part is equal to 1 divided by O small of theta, and this integral is divergent. So in some case we see that we may apply Taylor expansions, derivative moments, and it's not a big problem to investigate convergence of the or divergence of integrals. However, this is very beautiful result that if expectation is finite, then you know recurrency or transiency. Well, transient, if expectation of xi is not zero, transiency can be shown using other reasoning. We know by the law of large numbers that Sn divided by n converges to expectation, and if this not zero, then almost surely that Sn converges to plus infinity, almost surely Sn tends to infinity. And well, it is known from course of probability or from Markov chain that if the state is recurrent, then with probability 1 you have infinite number of returns. In this case, it's impossible. So if expectation is not zero, it's really easy to prove transiency. Well, but for recurrency, that's interesting. But as you may see, investigation of this integral, even if expectation of xi is zero, is not so clear, because all these numbers are real numbers. And you see, if we formally write this, we have real part of O of theta divided by O of theta, so this is 0 squared. And is it integral convergent or divergent? We don't know. If O of theta is real, then divergent, it's clear. But if it is complex, who knows? It is not obvious. And the last question is this. And what happens with, assume that expectation of xi is infinity. Is it possible that the random walk is recurrent? Well, the answer is yes, and you will have some exercises and the homework that sometimes expectation of Xi is infinite, but nevertheless, the random walk is maybe recurrent. Okay, that's all for today. Thank you for your attention. Are there any questions?